Welcome back to our Let's CTF series. Every month on the third Thursday of the month, we go through and talk about a CTF challenge that has been created, usually by me or my team, and sometimes by other challenges or other competitions, depending on feedback that we get from viewers and also kind of our own ideas of what we'd like to play around with. This month, we're going to be kind of extending some of the skills that we talked about last month, where we focused on Python challenges from the Pico CTF Pico Gym. This month, we're going to actually be creating a Python reverse engineering challenge. This is at request from a couple of people who've reached out and said that they wanted to know a little bit more about Python and about the creation process for capture the flag challenges. In order to create a new challenge, we need an idea of what skills we're trying to test for or kind of what we're trying to analyze. And so to do that, we want to set the stage for some learning objectives. What do we want somebody to get out of this from a learning perspective, since most of the CTFs that we generate here at Neuvik are kind of focused on that learning space. It's possible that they're just skill checks or otherwise kind of assessing somebody's capability. A lot of CTFs also do that as a way of kind of determining who out there has the best skills or is kind of best able to tackle sets of challenges or sets of problems. But typically, because I am the director of training here at Neuvik and we're generally creating training programs, our focus on the creation of these challenges is to teach some set of skills and kind of guide people along. So often we'll have a range of skills or that kind of goes from beginner up through intermediate to advanced in a single CTF, or we'll have sets of challenges per CTF and maybe a series of those. This is going to be a fairly intermediate kind of end of beginner. So it's still a beginner challenge, but with a little bit more knowledge about things like file systems. The goal here is going to be to know how to analyze a file that we receive, how to kind of determine what it is, what to do with it, and then a little bit of knowledge about Python as a programming language, and more generally about interpreted languages that do have some kind of intermediate phase. So what we're going to do here is we're going to actually supply a compiled Python program. And Python, kind of like many interpreted languages, actually does have an intermediate form between the human-readable thing that we interact with as we're writing the code and the thing that is interpreted by the Python interpreter. And it's somewhat similar to compiled languages in that way. When we're talking about compiled languages like C, C++, that sort of thing, typically those are going to be compiled to opcodes, to something that is executable directly by the CPU. And that's going to be something like Intel assembly. So C code gets compiled to Intel assembly. Python code can be interpreted line by line, and that is how things like REPLs work, that kind of execute loop that you're used to working with if you ever just type Python alone on the command line. But there is also kind of an efficiency that can be performed, particularly when you're creating libraries that compiles those things to a bytecode file. So if you've ever seen a PYC file, that's what we're talking about in those situations. There's lots of kind of ways to create those. If you create a library and import them, then the interpreter is going to create a bytecode compiled Python script for you. But there's also a module that allows you to do that that's built into Python. And that's what we're going to be using for this process. Something to be aware of for Python, and really many managed or interpreted languages that are similar to it, is that the file that's created actually has a large amount of metadata in it, including things like variable names. And so we can take that and we can kind of reconstitute something very close to the original file if we have knowledge of what the bytecode operations look like. This is different than something like disassembly or decompilation of C, in that we don't keep that kind of information around for C programs. So we don't know what a variable name was. We may not know function names, depending on the kind of symbol information we have, whether that is a non-stripped ELF or a PE with an associated PDB, portable debugging file in Windows. But when we're talking about things like Python or even some managed languages in the Common Language Runtime family, we're able to reverse that back and get a lot of that information. With all of that kind of background in mind, let's go ahead and jump over to our virtual machine where we're going to be doing the actual creation of this challenge. So I just have a tmux session going here where I've split it into 3 windows, and I'm going to use the one over here on the left to actually create the challenge. And I'm going to kind of use the right 2 as interpreters or as kind of bash things in order to kind of manipulate or interact with the thing as I go along. The first thing I'm going to do is come over here, there we go, and make a new directory for the challenge that we're doing. So this is Slithering, we'll call it. We'll cd into that, and while we're doing that, let's go ahead and cd into that in our other terminals as well, just so that everything's kind of in the same place. Now that we have that, we can start thinking about what other skills we might want in the Python analysis portion of this. This is a reverse engineering challenge at its core. We're getting a file, we have to determine what it is and how to interact with it. And so I'm going to kind of have some operations happening in here that are going to generate a flag from another file. Kind of similar to several months ago when we had that C example, we got something, we determined that it was XORed with a value that was also in our output file. Here we want some set of operations that have to be undone in order for the original flag to kind of be reconstituted or recreated. The goal there is to test people's ability to understand what's happening in operations and their opposites for things that can be kind of easily done in reverse. Some things, create an output or a result that you cannot regenerate the original from. Things like hashing algorithms do that. We want to do the opposite. We want to make sure that we have things that can be undone, that we can actually create a script that does the opposite of whatever we're doing to get the original flag back out from an encoded version of it. So for that, let's go ahead and just make something like encode.py. And inside of this Python file, we want probably some kind of functions and variable names that will be regenerated by this process of kind of analyzing that bytecode and uncompiling it. So I'm going to create a global here that's just called XOR value. And we'll say that we're going to XOR with a capital A, which is 41. It is a decimal 65, but it's a hex 41. And I'm going to make a function that's going to actually encode the thing. So encode flag, and it takes in the flag as an argument. And for now, we'll just put a pass in there. It's not going to do anything yet. It will be the thing that does that mutation later on. And then let's kind of throw in some of the standard stuff. If name is main, this makes it so that if we run this on the command line, it'll do whatever is kind of inside of this. And we'll say encode flag, but then we need to actually get that from somewhere. So let's say that we're going to read that from a file. Let's open flag.txt for reading. We'll call that fh contents equals fh.read. We could have done that all in one line, but I kind of like demonstrating some of the context-sensitive things like the with keyword here. That'll come out and it forces people that are reversing this, that are looking at it, to understand how that works and what it does. It's a very common idiom in Python, and so by putting it inside of the challenge and having people read it, either they're used to it or they'll see it and learn a little bit about it. So we read the contents of the file, and now we actually put that in contents.flag. So let's fix that variable name. So now we'll have a flag.txt that gets read in. It has whatever that flag content is, and then it's going to encode those contents. And then let's say we're writing that out to enc.text as we're going to do RB here because, sorry, WB here because we're writing, and there's the possibility that these aren't like printable characters depending on the manipulation that we do with it. And so we want to make sure that we're writing as bytes so that it doesn't do any manipulation of that. Just a Python-y thing with the way that it handles files being opened, whether for kind of binary or non-binary human readable format. So we now want to write that value back out. So we probably want encode flag to return something. So let's say encoded equals, and let's make sure that we return something here. We'll start with just returning the flag. Later on, we'll change that to be something else. So now we're opening this file to write it out to, and let's just go ahead and say fh.write the encoded flag. So now we know that we have a flag, we're going to do something with it. We are reading it in, we're mutating it, and then we're writing it back out. Now we have to decide a little bit, like, what are we going to do? What are we going to do with it that can then be undone? So this is going to be maybe some bitwise operations, but those need to be bitwise operations that are reversible. And the kind of most common one there is going to be XOR. If we're doing ORing or ANDing, then it's not necessarily reversible because if we have a 1 and we OR on a 1, then we get a 1. If we have a 1, we OR on a 0, we have a 1. So in both of those cases, we have different operations resulting in the same output. That's not really reversible, whereas XOR is. It's a symmetric operation. We can also do some other reversible operations like addition, subtraction, multiplication, and division. Those things can be undone because they produce deterministic output that can be reversed, unlike that AND and that OR operation. So we know that inside of encode flag, we can do those things. Let's go ahead and say, we get the flag, it is a string. And so we want to first do something with all of the characters of it. So I'm going to split that from a string into a list of numbers. So to do that, we're going to say that flag equals, and we're going to use a list comprehension here. So let's say ord I for I in flag. Very often I will also kind of have a interpreter going so that I can kind of, as I go along, make sure that the things that I'm putting in are in fact the correct Python, because I very often forget the very specific things. Oh, looks like I never installed IPython, so we'll just use the base Python interpreter here. I just won't have syntax highlighting. And I always forget that it's not linked aliased back to just Python here. Okay, so as an example though, I do want to make sure that the code I'm putting together for this list comprehension is right. Maybe I haven't written one in a while. And so if you're writing something, always safe to test. So let's just say input string here. And then I am doing the list comprehension of ord I for I in input, in A in this case. Oh, forgot my parens. What am I even doing? There we go. Or I for I in A. That's a parenthesis, not an underscore. There we go. We can see that that did in fact give us a list of integers. And those integers represent the ASCII values, or Unicode values actually, of those particular characters, the characters in the string input string. So that shows that if we kind of come back over here, this is giving us back a list of numbers, notably integers. That means we can do arithmetic operations on them using other numbers without having to worry about casting that to a different type. We've already converted that from a string to a list of numbers. So now I can do some kind of manipulation to each of those. And let's go ahead and just let's start throwing some out there. So we have the list, and let's say that we're going to do some more operations to it. So let's say I plus 1 for I in flag. Now we've added 1 to all of the characters in it. And if we were to convert that back to a string, it would turn an A into a B and so on. I think I'm just going to print that out as a list of integers, and they're going to have to kind of figure out that they need to convert those integers back to a string at the end. And that gives kind of another stage to that reverse engineering concept that we have. And also it makes it a little bit easier for me. I don't have to worry about the result of any of these numbers being in the ASCII range when I write them back out to a file, anything like that. It just is going to be a list of numbers. Great, super easy to deal with. So I've added 1 to it. Let's then say for every number in there, let's also multiply it by 3 for I in flag, and then XOR it by this XOR value. But let's only do every other character when we're doing that. So, well, let's start by XORing all of them. So again, let's take that list comprehension. Let's say I XOR value. There we go. For I in flag. So far we've added 1. So far we've converted to numbers, and then we've added 1, multiplied by 3, and then XORed by that XOR value. All right. So the next thing we're going to do is something that is going to be not to every number, because I want them to have to kind of look at them and go through a series of steps that they kind of think about as they go, and kind of can't just do trivially by manipulating every single thing. So maybe the third character, let's say flag 3 equals flag 3 XORed with 123, just because those characters came out of my fingers there. And so the now third character has been XORed with an additional value. And one of the key things that they're going to need to do is all of these operations need to be done in reverse to get the value kind of back out of it. Now that we have all of that done, let's go ahead and join that together. So flag is space.join flag, and that should give us back out just those numbers with a space in between them. Return it. We get the encoded value back down here, and then we're going to write that out. So let's save that. And let's go ahead and come over here and go ahead and create a flag.txt. Let's see. I don't know, let's say NEU1234, just as an example. And let's put that in flag.txt. So if I now look at the flag.txt, we have that value in it. If I am to then run my, let's see, I'm going to use Python 3.8 for this for reasons that I'll get into in a minute. If I then run that script, which we called encode.py, there we go, we get, yep, we do have an issue because of our typecast. So let's go ahead and, let's see, string expected, int found. So we could convert all of those to strings. That's one way to do it. We can also just join it together and then take that list and convert it to a string. I'm going to do another list comprehension here because that's one of the skills that we're really kind of showing to the person reverse engineering this. So flag is stir I for I in flag. Now we've converted each of those integers into a string, and now we can join those back together. Oh. So let's say flag equals that. Save the file, come back over here and try running it now. All right. Yep, okay. And because this is Python 3 and we're writing raw bytes to our file here, we need to make sure that we have that as the proper bytes-like thing instead of a Unicode-like thing. There we go. And so now let's run that script again, and we actually get an output. If we take a look at our enc.txt, we can see we have those numbers. So we've now taken the thing and we've encoded it. We know that our flag here is, there we go, NEU, our curly braces, and then 4 numbers. So if we kind of count that, that's 9 total. If we come up here, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like we might have a space or something at the end of that, but it should still be okay. Let's double check that just to make sure that that is the case. And it looks like, yes, we have a space that's causing that to be, to be the length that it is there. Perfect. So we have our encoded flag, we have our flag, and theoretically we can take those numbers and reverse those operations and get the flag back. The next step is going to be giving them something that is the compiled version of this. And in particular, I mentioned earlier that I'm using Python 3.8. That's because the tool that is most common for taking this bytecode and turning it back into Python code supports up through Python 3.8 currently. Other versions are kind of going to come in the future. Rather than give them something that they have to get hands-on with, I want to give them something that there is a tool for. So here I'm using Python 3.8 because I know that the bytecode that is generated by Python 3.8 is something that can be undone by the tool that I'm going to be using. To get a compiled version of it, I need to run pycompile here. That is just a module in Python that will create that bytecode. And I'm going to pass into that my encode.py. Oh, there we go. I wanted Python 3.8, I said. So now one of the things that we're going to see is it creates this PyCache folder. And if we look inside of that PyCache folder, we can see that we have Python, CPython, and then -3.8. So that's telling us what version or what kind of Python interpreter we have. Here we have CPython. It is the Python interpreter implemented in C. That's the most common Python. If you just install Python on the command line or download it, you're going to get CPython. That is in contrast to, for example, Jython, which is a Java implementation of Python, or some others. There's a Lua implementation, things like that. The most common, though, is going to be CPython. And we can also see that we have 3.8 here. That 3.8, that's just telling us the version that we have. If we'd compiled this with Python 3.10 or 3.12, we'd kind of see those numbers. And we can demonstrate that as well by redoing that same operation with Python 3, which we can see on my system is Python 3.10. So that contrasts with the Python 3.8 that I invoked up here. And so that kind of difference is going to be important here in a second. When I come down to here, I no longer need that. I have uncompile, which is a tool that takes Python bytecode and turns it back into a Python script. So I'm going to uncompile the encoded 3.8 version, and we can see that it prints that out. If I want to put that into a file, I absolutely can, and I can say that that is output.py. Now, if we look at output.py, then we can see some comments kind of up here at the top, but then we also have that same code. Looks very similar to what we have over there on the left, right down to the variable names, the operations are global, things like that. So that is kind of what a challenger, somebody kind of going through this, would do. But we don't want to make it quite that easy for them. We don't want it to be obvious that it's just that step and then reversing those operations. So when I actually deliver that PYC file as a part of this challenge, I would do that without the file extension. That's really not going to be a huge challenge to them, because the first thing that someone getting an unknown file is going to do is determine what that is. And we can do that just using that file utility on Linux. So if I do file pycache encode cpython 3.8.pyc, it's going to tell me that it is a Python 3.8 byte compiled file. If I do the 3.10, that's going to say data. And that is because the magic numbers and some of the other things that we see there are a little bit different, and the file utility hasn't been updated with that newest thing. So that's another reason I used Python 3.8 instead of 3.10 or some other version. I want something that's kind of easy, straightforward for somebody to take a look at. If we come over here, we can also kind of see what those files look like as raw data. I'm going to open it in Vim despite it not being like a human readable file. We could also open it in something like a hex editor, but I have Vim open over here, so I'm just going to do that. Let's see. And then encode.cpython 3.8.pyc. So if we take a look at that, as we can see, it is not human readable. It is a binary file because it is bytecode compiled. But we do have some things in here that we can kind of see as a human. So in particular, we know that we have list comprehension here. That's interesting. We have a variable name here, XOR value. And so one of the things that I would often do if I wanted to have multiple flags here is that I might create a variable that is a flag as its name. And that way, if somebody was to run like strings on this, they would see that even before they determined that this was a Python bytecode file or anything like that. And we can even kind of demonstrate that by saying, let's run strings on that encoded file. So just getting series of bytes from the file that look like printable characters, we can see that we got several of those values right back out, like our XOR value, like our encode flag function, the file names that we had in there as string constants. All of those are human readable even in the binary format, they are a series of bytes that are printable. And that's really all the strings utility is looking for. By default, it's looking for 3 or more in a row, but that's also configurable with command line switches. So again, that next step would be to take that file, encode.cpython38.pyc, and I'm going to just, well, let me copy it instead. I'm going to say, take that, and let's copy that and say challenge. So now in our current directory, we just have something called challenge. And if you were given that in a CTF and said, hey, here's a file, figure it out, the first thing you're going to do is see if you can just determine the type. And we can. We can determine even without that file extension, using magic numbers, using metadata inside of the file, that it is in fact a Python 3.8 byte compiled file. And then we can come down there, as we kind of saw with the uncompile 6 utility, and we can turn that back into Python code. We can look at that Python code, and we can determine these are the operations that were taken to convert from a flag file into an encoded file. And we can undo those same things. So again, coming over here, if we take a look at the encoded Python here, just the operations that are happening, we're going to then do those in reverse order. So we see that they are joining it and they're converting it to a string. So we know that it needs to undo that. We don't necessarily know if we're just going in reverse order what those types are. So we do kind of have to read all of this as a block first, and we can see that the manipulation is being done based on the ord of that. So they are integers. So the combination of knowing that they're joining it at the end and that they split it at the beginning into integers tells us that the rest of these operations are going to be on integers. So we know that we need to XOR the third item of each number with 123. And then we need to XOR again with 0x41, then divide by 3 to undo multiplication, subtract 1 to undo addition, and then convert via the opposite of ORD, which is going to be the CHR function. So if we were to create our reversed version of this, that's all we'd have to do. Take it, split it on spaces into numbers, convert those to integers, and then do those operations. So let's go ahead and do that over here in a Python interpreter. This time, because we are just executing code, it doesn't matter if we're using Python 3.10 or if we're using Python 3.8, as long as we're doing something that we ourselves understand how to write in. So I'm going to say the first thing that we need to do is read in the encoded version. And we called that, let's see, enc.txt. I'm going to RB, read as binary data here. Again, because that might not have been human readable. We actually know that it is. It doesn't have any special characters in it. It's just within the ASCII range. So this B is not strictly speaking necessary. But if we're reading kind of raw data that's handed to us, I typically will use it. And then we're going to use as FH. That's just kind of a convention. The FH stands for file handle. We could call that anything. And then we're going to say, let's say encoded is fh.read. And so now we see we have, because we read that out as binary with that B, we have these things. So let's go ahead and decode that. So let's say encoded equals encoded.decode. This is just converting it from a byte string into a Unicode string, the default string type in Python 3. So now we see we have those same things. Let's go ahead and split that on spaces. So the encoded list equals encoded.split. So now we can see that we have a series of strings of numbers. Let's convert that to integers. So that's, I'm going to do int I for I in list. Again, using a list comprehension just because that's a really easy way to do this. We could also use the map function, but that is deprecated. So instead of that, we're just going to do that. And so now list, there we go, is a list of numbers rather than strings of numbers. Now for each of these, we need to undo those operations that we saw. So in the same way that we were doing list comprehensions to create this list, let's undo them using list comprehensions. So we saw that we, coming over here, need to XOR with 123, because the opposite of an XOR is actually XORing with the same thing. That's how we undo that. So we want actually, sorry, the first thing we want to do is just the third element. So we want to say inc list 3 equals inc list 3 XOR 123. We don't want to do the entire thing, just that one element, because we're undoing each thing step by step. But the next thing we want to do is a list comprehension of the entire list. So now we want to say I XORed with XOR value, which we can see was 41. So we can just put in a 41 here. 0x41 for I in inc list. So we've now undone the XORing of that XOR value. Now we need to divide by 3. Because we were dealing with integers and we multiplied by 3 and we're now dividing by 3, we're going to get integers back. So I could do truncating division or non-truncating division. So I know I'm dealing with integers. My instinct is to do truncating division, but it doesn't actually matter here. We're going to get back an integer value anyway. And so we want to divide by 3 for I in inc list. All right. And let's take a look at what we've gotten so far. So by doing that, we can see that it did convert them to floats. That is something to kind of be aware of. I did that divide by 3 instead of an integer or a truncating division for that reason. Let's see kind of what the result we get out is and whether that's still useful. All right, so we divided by 3. Now we need to subtract 1. So inc list, once again, equals I minus 1 for I in our list. And then we need to take that and do the opposite of our ORed function, which is going to be CHR. So let's do just one element of that. There we go, item 0. We can see that we do have a problem because of the way we converted that and it caused it to be a float. So I said a little bit like it doesn't matter. It actually does because of this conversion between ASCII values and strings or characters. And so because we made that kind of quote unquote mistake there, let's undo it. Super easy to do. All we need to do is make sure that those floating values are actually integers. So we can do int I for I in our list. Oh, helps if I have my equal sign there. And now our list has integers and we can convert them. So let's go ahead and do that. Our list is going to become CHR of I for I in our list. And that on its own will give us a list of those characters. I could absolutely take that along with the stripped new line that I don't want. I could absolutely take that and I could type it manually in, but I can also just say, hey, let's combine that without anything between it. And that prints it out for me in something that I can just go, hey, okay, let me copy that. And I can paste that into CTFD or wherever that challenge was. So we have now created and solved this Python reverse engineering challenge. I hope that that was useful for you. I hope that kind of the process of ideating or coming up with the concept was straightforward, the learning objectives that we're trying to get across here, and all of those steps and stumbles along the way. You know, creating challenges takes time. This would not be a complete challenge on its own. The next step for this would be something like, you know, writing up a write-up for it. So we would say this is how you create a new flag. We'd want to make this kind of dynamic and programmatic in the creation of that rather than having that hard-coded flag value. We'd also want to make sure that we had instructions for the competitors and that if somebody other than us is running the CTF, they know what the solution is, how to solve it step by step so that we kind of have a solve script or a solve process that they can use to help those competitors, help those challengers, and maybe even write up some hints that we can put into our CTF platform, whether that is CTFD or something else. But the kind of main body of it, the creating the code and kind of determining what we're going to give them in that, you know, unnamed file that they have to do the reverse engineering for, all of that is done. And it was pretty straightforward. So I hope you enjoyed this. I hope you got something out of it. Next month, we'll be taking a look at another challenge. If you have some particular set of skills you'd like to look at or anything along those lines, feel free to reach out. And failing that, I'll pick something and we'll work on that next. Thank you so much for joining me, and we'll see you next month.